Look up on any given day, and you'll see a shifting display of color. A deep midday blue bleeds into vibrant sunset reds, and under the right atmospheric conditions, you might even catch a rare emerald green flash right on the horizon. We often speak of the atmosphere being painted with different pigments, but solar emission is entirely white light, a complete, unbroken blend of every color in the visible spectrum. This diagram shows the process of extinction. To produce a specific color from a white beam, the atmosphere must physically subtract specific wavelengths. When the green and red bands are stripped away, only the isolated blue remains to reach the observer. The vibrant hues we see overhead represent the light that the atmosphere rejected. We define the sky by what it allows to pass through. Midday theometry determines the first layer of subtraction. With the sun directly overhead, light takes the shortest, most direct path through the Earth's atmosphere. As the beam enters, it strikes nitrogen molecules, triggering Rayleigh scattering. These molecules selectively catch the shortest blue wavelengths and scatter them in every direction, filling the dome of the sky with a blue glow. As the sun approaches the horizon, the atmospheric path lengthens significantly. Along this extended journey, blue light scatters so thoroughly that it is entirely depleted before reaching your eyes, leaving only the long wavelength red to survive the trip. A brilliant red sunset serves as visual proof of these global-scale collisions. The red wavelengths reach us precisely because every other color was deleted along the way. While physics explains the light arriving at the pupil, the second layer of extinction occurs within the biological hardware of the eye, especially when staring directly at a bright red horizon. Our retinas rely on light-sensitive cones. Exposure to intense red light quickly fatigues the L cones, chemically exhausting the cells until they lose the ability to signal the color red. Opponent process theory explains how our vision maintains balance. When the red channel is exhausted, the internal seesaw of the eye tilts. The brain perceives a sudden spike in the opposing cyan or blue channel, creating a phantom negative afterimage that overlays the environment. This internal biological fatigue likely explains rare horizon anomalies. High-altitude sites like the Paranal Observatory in Chile provide the clear conditions necessary to witness these momentary blue and green flashes as the sun disappears. The human mind manufactures these colors by subtracting physical reality. We see the flash because our eyes have temporarily deleted the sun's actual color. Once the sun sets, Rayleigh scattering ceases and biological fatigue fades. Logically, the sky should turn a colorless gray. Yet, during twilight, a distinct, deep blue emerges. In 1952, physicist Edward Hurlburt used photometric sensors at this observation tower in New Mexico to investigate this phenomenon. His data proved that physical scattering alone could not account for the intensity of light during the blue hour. Hurlburt identified the cause as Chappuis absorption. This spectrum shows how the stratospheric ozone layer functions as a chemical sponge, specifically trapping yellow, orange, and red light. The deep twilight blue remains because the ozone layer has scrubbed away the warm side of the spectrum. We see only the blue light that the ozone failed to absorb. Energy cannot be destroyed, only converted. This raises a thermodynamic question. Where does all that trapped energy from millions of miles of subtracted sunlight ultimately go? The answer exists at a much smaller scale. If we zoom past the vast layers of the atmosphere, we eventually reach the microscopic boundary layer of a single cloud water droplet. At this interface, absorbed visible light acts as a catalyst. When ozone molecules on the droplet's surface are struck, photolysis physically fractures their bonds. The oxygen atoms interact with surrounding water, generating hydroxyl radicals, OH radicals, that are released into the troposphere. While this happens on a single droplet, clouds provide a high surface area to volume ratio, turning them into vast distributed chemical reactors. These OH radicals act as a global detergent, oxidizing compounds and neutralizing pollutants across the atmosphere. Every hue we see in the sky, from midday blue to the blue hour of twilight, marks a moment where light energy was diverted to power this atmospheric cleansing. The colors of the sky are the visible exhaust of a world-scale air purifier.